All right, let's jump right in. Today, we're going to pull back the curtain on the invisible forces that move heat all around us. We're talking about the hidden physics that explain everything from why your bathroom floor is so cold in the morning to how the sun warms your face from millions of miles away. Okay, so let's start with a mystery that I'm sure every single one of us has experienced. You hop out of bed, your foot touches that tile floor, and wow, it feels like you've just stepped on a block of ice. But the carpet right next to it feels perfectly fine. But here's the twist. A thermometer would tell you they're the exact same temperature. So what's the deal with that? Well, the answer to our little floor mystery, and frankly a whole lot more, comes down to these three fundamental ways that heat gets around. Think of them as the secret instruction manual for energy. And believe me, once you learn to spot them, you'll start seeing them absolutely everywhere. First up, we've got conduction. Now, the easiest way to think about this one is like a direct energy handshake. It's a physical, molecule-to-molecule passing of heat. The key phrase here is direct contact. Conduction can't happen without it. It's basically a chain reaction of jiggling molecules. You heat one up, it starts vibrating like crazy, bumps into its neighbor, passes on the energy, and so on right down the line. We've all done this, right? You leave a metal spoon in a piping hot pot of soup. The heat doesn't magically jump to the handle. Nope. It travels, molecule by molecule, all the way up the spoon until, ouch, you grab the handle and realize just how hot it is. That, my friends, is pure conduction. And that brings us right back to our floor mystery. Tile is a fantastic conductor, so when your warm foot touches it, the tile yanks that heat away from you super fast, which your brain interprets as cold. Carpet, though, is a terrible conductor. We call that an insulator. It's fluffy, it traps air, and it slows that heat transfer way down, so your foot gets to keep its own warmth. Same temperature, totally different experiences. Okay, on to our second mechanism. We're shifting gears from solids to fluids now with convection. This one is all about literally riding the heat wave. Now here is the huge difference. With convection, it's not just the energy that's on the move, the substance itself is moving. Hot air or hot water physically goes from one place to another, carrying all that thermal energy with it. And this is the engine that makes all convection go. It's a universal rule of physics. You heat up a fluid, air, water, whatever, it expands, it gets less dense, and it starts to rise. This one simple process creates enormous movements of energy all over our planet. Just picture that pot of boiling water again. The burner on the stove heats the water at the very bottom. That hot water rises up, and as it does, the cooler, denser water from the top sinks down to take its place. What you get is this rolling, circular flow called a convection current. You are literally watching heat circulate. And this isn't just happening in your kitchen. On a massive scale, convection creates those pockets of warm air, thermals, that glider pilots use to stay aloft. It's what pushes moisture high into the sky to form clouds, and it's even a major driver of the winds that circle our entire globe. All right, time for our third and final player, radiation. This is the big one. This is how the sun's incredible energy travels 93 million miles through the cold, empty vacuum of space to warm up our planet. Now, unlike conduction and convection, radiation is special. It doesn't need a medium. It doesn't need molecules to bump into or fluids to flow through. It can travel right through the total emptiness of space, which of course is how we get any energy from the sun at all. And how fast does it travel? Oh, just at the universe's ultimate speed limit, the speed of light. That's an insane 300,000 kilometers, or about 186,000 miles, every single second. So what is this solar energy exactly? Well, if we break it down, we see that almost half of it is infrared. That's the stuff we feel as heat. Another big chunk, 43%, is the visible light that, lets us see things. And that small but mighty 7%, that's the ultraviolet or UV radiation that can give you a sunburn. Now, the sun is a powerful example for sure, but it's not unique. Radiation follows a very strict set of rules that apply to every single object in the universe, including you. So let's take a look. So here's rule number one, and it's kind of a mind bender. Absolutely everything is always radiating energy. The sun, the earth, the ice caps at the poles, your coffee mug, you name it. If it has a temperature above absolute zero, it is constantly sending out waves of energy. This little comparison chart shows us the next two rules perfectly. First, hotter things radiate way more energy than cooler things. You can see the sun's output is massive compared to Earth's. And second, hotter objects radiate energy at shorter, more powerful wavelengths, so the super hot sun's energy peaks as visible light, while the much cooler Earth radiates in the longer, less energetic infrared spectrum. And the final rule is pretty straightforward. Things that are good at absorbing radiation are also good at emitting it. Earth's surface, for example, is fantastic at both. It soaks up the sun's shortwave energy and then radiates its own long-wave heat right back out. Our atmosphere, on the other hand, is what we call a selective absorber. It lets the sun's light pass right through, but it acts kind of like a blanket, trapping some of the heat that the Earth tries to send back out. And there you had it, from the spoon in your soup to the winds in the clouds, all the way to the sunlight hitting your face. Conduction, convection, and radiation. They're the invisible forces that are constantly at work, shaping our world every single second. And that's really the cool part. The next time you feel a breeze on your skin, or see steam rising from your coffee, or step onto that cold bathroom floor, you'll know the secret physics behind it. So my question to you is, now that you know the rules of the game, where are you going to spot these invisible forces at work next?